In previous videos in this series, we've looked at some introductory ideas in Riemannian geometry involving flat and curved spaces, the metric tensor, and ways of transforming from one frame of reference to another. And this necessarily involved aspects of differential geometry, which makes use of traditional ideas of calculus and differentiation. However, we now want to introduce the idea of a different kind of derivative, if you like, a new way of differentiating things, and it will be called the covariant derivative. It's needed because of all the things that have been discussed so far about the metric tensor and curvilinear coordinates. Before we begin to investigate how such a thing might come about, let me simply state what this new covariant derivative will look like and how it will be different from the usual way of differentiating things. Suppose we were working in two-dimensional space and we had a vector v at some point in that space, at the black dot, say here, at the intersection of these two angled axes, x1 and x2, and let's assume that the vector is contravariant. It could be the velocity of something at the point, although as usual we'll illustrate it by adding the extended arrow shown here in green. This vector could be said to have two component vectors, shown now in orange and with upper indices, and these component vectors will add up to v vectorially. From what we have already discussed, each of these orange component vectors could also be broken down into a measured scalar value, what we've been calling the component or the component measure, multiplied by the appropriate basis vector of the frame of reference at that place. In this case, we're looking at the contravariant components, those with upper indices, and the formula for the vector would then be written like this: v equals v1 plus v2, where v1 is v1e1 and v2 is v2e2. We realize that if these component vectors varied over the space, then the component measures of them might not vary in the same way. And this would be because the basis vectors might be changing from place to place. We could even have the bizarre situation where this vector did not change with position. In other words, the two component vectors remained unchanged, and yet the two measured components change with position. This could possibly go up and this one down, all because this basis vector went down and this one went up. If the vector itself did change with position and say both these component vectors increased, then these measured components could go bigger or smaller or stay constant, depending on what the basis vectors are doing at that point. All this would mean that if we were simply to measure the rate of change of these component measures, for example the partial differential dv1 by dx1, which is all we could measure with our measuring system, it would not necessarily be equal to the rate of change of the size of the component vector itself. This is the measured component v1, but this is the component vector v1. In other words, size-wise, or rather in terms of the magnitude of things, this relationship would not be true, which is the same thing as saying that this would not be true in terms of the magnitude of each side of the equation. Or perhaps we should write this with just the size of E1 rather than having it in bold as a vector, and say that this relationship would not necessarily be true. It seems that if you want to use the simple and straightforward method of taking the derivative of the measured value of the component, the simple dv1 by dx1, you would get the wrong answer for the way the actual component vector is changing, and you'd need to make some sort of correction to it in order to allow for the changes in the basis vectors, and that means to allow for changes in the metric tensor. That is, if you want to know the actual way in which the size of the component vector, the orange v1, was changing with position. Well, what we are going to call the covariant derivative will do just that. It will make the correction. In this example of looking at dv1 by dx1, the covariant derivative will be written like this: capital dv1 by capital dx1. And notice those capital D's instead of the small d's or delta. This is just one of the ways in which the covariant derivative is distinguished from the ordinary derivative, although there are other ways of writing it. And if you've not met this kind of thing before, it is bound to look rather strange. And we're going now to try to make sense of it in a moment. In very simplistic terms, it could be said to be this, the real way in which the component vector size changes with position x1, because this is just that, the real way in which the component vector size changes with position x1. This could be written, of course, like this, as the measured derivative plus some positive or negative correction term. Now, before we try to understand a little more about the covariant derivative and the correction term within it, let me state the whole thing in the Einstein Summation convention form. It is this: for the derivative of the contravariant or upper index components of a vector v. Basically, this covariant derivative is equal to the usual derivative of the measured contravariant component, which we know is wrong, plus a correction term. And that correction term contains the measured component and this gamma term. Gamma is known as the Christoffel symbol, and basically, along with the v term in front of it, it adds or subtracts, if it's negative, what is needed in order to take into account the changes in the metric tensor over the space. The Christoffel symbol, gamma, can be written in summation form like this. Okay, granted, these equations look horrendous, and they can be when you come to have to calculate them. However, we should be able to get a reasonable understanding of them. You should be able to get your head around them, and hopefully we'll do that in a moment. What you can see here already is that this Christoffel term, this correction term, or connection as it's sometimes called, is all to do with the metric tensor and how it is changing from place to place. And that's as it should be, I suppose. When the Christoffel term is multiplied by the component measure VR, it becomes the amount needed to modify the derivative of the measured component in order to allow for changes in the metric at that point. The answer, after that modification, will be the actual derivative of the way the size of the component vector changes, which we call the covariant derivative. We won't discuss these things in any more detail at this point, but rather we'll start from scratch and try to see where the bits and pieces come from and what they mean. And to keep things simple, let's look at a one-dimensional situation. Now, what follows immediately will not be a proof of the covariant derivative formula or in any way rigorous, but hopefully it will help us gain some understanding as to how it comes about and why it has such a strange look to it. Consider then the one-dimensional flat space shown here, which has the axis x1. And suppose for the moment that the metric or measuring stick for this is a simple linear scale with unit basis vectors throughout. There's no stretch or compression of the scale. These basis vectors are all equal to 1 and are shown here offset for convenience. This is the equivalent, I suppose, of Cartesian coordinates being used to measure a flat Euclidean two-dimensional space, but it's in one dimension. Imagine also that there is a vector v at some point in the space, at say the 0 point, at this black dot. We'll add the green arrow slightly to one side of the line to illustrate its size, but assume that the vector exists at the black dot. In order to be a little specific, let's say it is a contravariant vector such as a velocity, something with x on the top of its formula. If we were in 2 dimensions or more, we wouldn't have to be specific about the vector itself, as we'd be able to think in terms of the contravariant and the covariant components of the vector, whatever kind of vector it was. And so we could simply pick the contravariant components of the vector. However, here, with one dimension, in a way, the component vector is the vector. So we'll be specific. It's a contravariant vector, a velocity. And for that reason, we'll call it not just v, but v1 upper. In a sense, it's only got one component, a contravariant component, because it is a contravariant vector. Let's suppose also that this velocity has different values at each point along the x1 line. The vector v1 seen here would then be the velocity vector at that 0 point, at the black dot. The other points on the x1 line would have their own possibly different velocity vectors. And if the velocity does indeed have a different value at different points along the x1 axis, then we can talk in terms of the rate of change of the vector with distance or displacement, dv1 by dx1, at each place. This kind of derivative at each point in the space is easy for us to work with using calculus. If we wanted to use first principles to find out the derivative of the vector at the point 0, at the black dot, we would consider a second point a short distance dx1 away from that position, and say that the vector there would be slightly different, let's say bigger, like this, where I've rather exaggerated the change in size so we can appreciate it, and I've drawn it on the other side of the line for clarity. We can then imagine detecting the difference in the size of the vector by comparing their lengths. We only have one dimension after all. We could illustrate that difference in this diagram by imagining shifting the new vector backwards to the 0 and then measuring dv1, the amount by which the vector has changed over the distance dx1. So this is our situation. The division of dv1 by dx1, after we let the values tend to 0, is the rate of change of the vector with distance at the point under consideration. It's basic high school calculus, and there's no need to use partial differentials here in this one-dimensional situation. We could even get this same kind of result and see some insight perhaps if we said that this vector v1 shown here in bold is really the size of the vector as measured in this frame, not bold, multiplied by the basis vector at the point under scrutiny. Remember that all this is taking place at the point because dx1 will tend to 0. Remember too that in this particular case we said that the metric being used, or the measuring stick for this situation, is a simple linear scale. It has unit basis vectors throughout, and so the modulus or magnitude of this particular v1 is equal to the measured size of the vector v1, at least in this particular frame of reference. Now, to find the derivative of this whole vector v1, we could differentiate this equation using the product rule, and we would get these two terms. But of course, this particular metric or measuring stick is linear. Its spacing, for want of a better word, is the same everywhere and doesn't change, so the basis vector, e1 in this case, is constant, meaning that this term disappears, leaving us with only the first term. This equation now simply says that with this unchanging metric, the rate of change of the vector v1 with distance is equal to the measured rate of change of its size with distance, multiplied by the direction vector e1, of course, which is, in this case, is the constant value of 1, and simply gives us the direction plus or minus in this particular case. Again, this answer makes the assumption that the metric is unchanging or constant, that there is no differential stretching or contracting of the scale anywhere, so that the basis vector e1 is the same everywhere, and this all means, in this case, that the rate of change that you measure is indeed exactly equal to the rate of change of the magnitude of the vector. All very simple. Now, I have rather laboured that point in order to highlight the importance of the idea of the covariant derivative, which we will now start to work with, and we'll work it out from scratch in one dimension. Consider the same one-dimensional space, but this time we'll measure it using a metric which is not constant, but which is changing. We'll assume that the space itself is flat, but that's not quite the issue here. It's the measuring stick, the metric, which is now in a sense stretched or compressed in different places. Here's a possible illustration of such a metric, of such a scale. Again, there are no numbers on the scale except for the 0, which is only there for convenience, but the variable spacing is meant to represent the fact that it is now a non-linear scale. We have basis vectors that are changing over the space, bigger here, smaller here, and so on. And you could say that we have curvilinear coordinates but in one dimension. So let's now consider the same contravariant vector v1 as before at the 0 point. Remember again that this vector, which could be a velocity, is on the black dot at the 0 point, and the extended green arrow is only there for us to appreciate its size. Consider also that this vector changes with distance, so that we could again draw its actual size slightly larger, say, at some distance dx1 away, and we could go through all that calculus argument once more. Now let's ask the same kind of question as we did before. What expression could we write down which would best describe the actual derivative of this vector, its actual rate of change of size with distance? I'm sure you realise that it would not necessarily be the same as the measuring scale would tell us. That scale is stretched and compressed in different places, and so measurements made using it will be too small when the scale is stretched and too big when it's compressed. That's just the property of contravariant vectors. And this will mean that the measured derivative, the way the vector is measured by the scale to have changed with distance, will not necessarily be the actual derivative of the vector itself, the way its size actually changes with distance. And in order therefore to get a sensible idea as to what we could write down as the derivative of the vector, its rate of change with distance, we can't simply measure it using the scale. We will need to include not only how the size of the vector is measured within the reference frame, but also how the reference frame itself will measure things differently. And as you'll see in a moment, we will need this time to keep the second term in our differentiation. So here once again is our depiction of the contravariant vector v1 in terms of its measured size and the basis vector at the point where it happens to be. It should be obvious that the modulus of this v1 here has a size equal to the actual size of the vector and is independent of how you measure it. But this v1 is the measurement made by the reference frame, which could be bigger or smaller depending on the basis vector at that place. So let's differentiate this whole thing by the product rule and get the two terms once again. And let's put in v1e1 for this vector v1. In this particular case of working in one dimension, the directionality in this equation is not really in question except for being positive or negative, and so for convenience let's take away the vector nature of it and we'll write the e1s simply as scalars, in other words, the size of the basis vector at each point. Remember, this is the actual derivative of the size of this one-dimensional vector, and this is the derivative of the measured size of the vector, and this is part of the correction term. Now let's divide throughout by the value of the scalar e1, and this will give us this equation. We now have on the left hand side what we might call the actual derivative of the size of the vector divided by the size of the basis vector at that point. And if you think about it, that whole thing must be equal to the actual derivative of the component v1 of the vector. Think about it. It's the actual size of the derivative of the vector divided by the basis vector. And so it must be the actual derivative of the size of the component of the vector. And if we now call that the covariant derivative of the component and write it like this, it should hopefully be easy to grasp the meaning of this equation. This is the actual rate of change of the component of this contravariant vector with respect to distance in the x1 direction. The value of this does not depend on the reference frame being used to measure it. Any reference frame will give this same answer. This, on the other hand, is the rate of change of the component of this contravariant vector with respect to x1 as measured by the reference frame. If this is bigger than it should be, it will be because the scale has shrunk, and in that case this extra term will be negative to give the correct answer on the left. If this is smaller than it should be because the scale has stretched, then this extra term will be positive, again, in order to give the correct answer on the left. This idea of the covariant derivative is extremely important in general relativity. When we come to look at vector fields and how they change with distance, it's not so much knowing how they are measured to be changing by some strange curvilinear coordinate system that matters. We need to know what is really going on. We need to know how the vector fields are actually changing. And for that reason, we will always be using the covariant derivative. However, even this one-dimensional form of the covariant derivative doesn't look particularly friendly. What's this, for example? What is this extra term which adjusts the answer for the changing scale, or rather the changing the metric? Can it be written in another way? Well, we've said that it's a measure of the way the curvilinear coordinates stretch and contract, so it must have something to do with the metric tensor. And if we now work through some rather simplistic mathematics, it should, I think, help you to appreciate the covariant derivative more clearly, and also the idea of Christoffel symbols. Thinking in one dimension here should be helpful for when things get much more complicated and we start to have to think about more dimensions. So let's investigate this term for this one-dimensional situation. You should recall or realize that a one-dimensional space only has one term in its metric tensor, G11, and it's given by the dot product of E1 with itself at the point under scrutiny. In other words, G11 can be written as simply the size of the basis vector squared. The dot product of a vector with itself is simply its magnitude squared. It's a scalar. In the situation that we've been looking at, of course, this G11 is now a function of position because E1 itself is assumed to be changing with position. This means that we could now take this last equation for G11 and differentiate it with respect to x1 using a function of a function. And we would then get this expression, which by rearranging means that we can write dE1 by dx1 as this. Substituting this dE1 by dx1 into the expression for our new one-dimensional covariant derivative gives this. But of course E1 squared is G11, the metric tensor, and so we can rewrite this again as this. Furthermore, we could, if we wanted to, put this G11 on the top line, providing we change the indices to upper indices so that it's a kind of inverse of G11 lower. Now there's nothing new here. This is the derivative of the component of the vector at the point as measured in the frame of reference, and will be different in different frames of reference. This is the term representing how the basis vector changes at that point, and will again be different for different frames of reference, different G11s. However, add these together for a given frame of reference, and you will always get the same answer for a given vector. This is the actual derivative of the vector component at that point, independent of how you measure it. It is what we call the covariant derivative, and is a property of the vector in the space, and does not depend on the reference frame used to measure that space. We can even hint at the more complicated idea of Christoffel symbols. For example, if we take our one-dimensional equation, we could replace all of this with a single term, gamma, to stand for the multiplication of these three numbers at the point. Now, on account of the fact that we had a number of indices, three of which are very important, we could write it as gamma 111. But it's just a constant. It's just a constant at that point, which depends on the metric tensor and how it is changing at the point. Now, although the mathematics used here may not have been entirely rigorous, and this shorthand might seem a bit strange, You should really think carefully about this result and let it sink in. It is quite a simple idea in many ways, at least for one dimension, if you're prepared to spend a little time thinking it over. Getting your head around the concept of the covariant derivative and this simple expression for it in one dimension, which includes the metric tensor g11 and its derivative, should then be helpful when, in a moment, we make the massive step from one dimension to two and then on to more dimensions. Seeing this version of this covariant derivative in one dimension and accepting the rather loose proof of it, which we've just done, should allow us to accept the more complex looking expressions for the covariant derivative which will have to be used in higher dimensions and which will become increasingly more important as we get into general relativity. Remember that what I'm calling the ordinary derivative of the component is what someone in the space would measure by using their particular frame of reference, and it probably won't be how the actual component of the vector changes with position. The covariant derivative of a given vector at a particular point, on the other hand, will always be the same, no matter what frame of reference is used, because it will compensate for that frame of reference. In this way, it will be a useful kind of derivative for the equations of general relativity, the differential equations of general relativity. Now, perhaps a natural question at this point might be to ask, why is it called the covariant derivative? What's covariant got to do with it? Well, we'll try to answer that question at a later time, but quite understandably, it can sound strange here that we've been taking the covariant derivative of a contravariant vector component. You should try at this stage to see past the language for the moment. Take it that we have simply found a useful and sensible derivative which takes the metric and any stretching into account, and we just happen to be applying it here to a contravariant vector such as a velocity. We'll get to how the covariant derivative can be applied to covariant vectors, or rather covariant components of vectors, in a moment when we move to thinking about two dimensions. Two-dimensional situation, when we get to it, will inevitably have more complexity than the one-dimensional situation that we've just discussed. For obvious reasons, in that one-dimensional equation, dv1 by dx1 only contained ones in it, v1s, x1s and g11s. But once we get to two dimensions, even dv1 by dx1 will have to contain something about the x2 direction as well. On top of that, it will also have to involve v2 as well as v1. This is because of the fact that the two directions affect one another. As we illustrated right at the beginning of this video, things are going to get quite messy. However, once the two-dimensional situation is done, we can write the result in the Einstein Summation convention, and that can then be used to show the expressions for three or more dimensions. Let's therefore now move on to thinking about the covariant derivative for two dimensions, which will obviously involve looking at a number of components of a given vector, how they're measured to change, and how they actually change. Don't forget that in simplistic terms, we want an expression that will stand for what I've been calling the actual derivative of the component vector, its differentiation with respect to displacement in some direction, and the final answer must not depend on the kind of scale or metric being used to measure it. Consider therefore a flat two-dimensional space. We're still not looking at curved spaces yet. A flat space which is being measured using curvilinear coordinates x1 and x2, coordinates which probably stretch and compress in different places and which also will change their direction. Consider also that there is a vector v at the point shown here, at the black dot. We don't have to stipulate in this two-dimensional case whether the vector is contravariant or covariant. It could be a contravariant vector such as a velocity, something with x on the top of its formula, or it could be a covariant vector such as a field with x on the bottom of its formula. Either way, we can focus on its contravariant components if we wish, or of course we could consider its covariant components. Remember again that the vector is at the point where the black dot is, at the base of the green arrow shown, and we want to investigate some kind of useful measure of the derivative of the vector with respect to displacement in either the x1 direction or the x2 direction. Looking at this vector and this set of coordinates, we can say that at the point infinitesimally close to the black dot, the coordinate lines are essentially straight, like these black dashed lines, and they follow the tangents of the axes at that point. And so the situation at the point essentially looks like this. Let's now consider the contravariant component vectors of this. These are the two vectors which will add up to the vector v in the usual way, and they are shown here in orange. The lengths of these orange vectors here represent the actual size of the contravariant components v1 and v2, and the mathematical representation of this addition is simply v equals v1 plus v2, where v1 is v1e1 and v2 is v2e2, and so we can write this vector equation, v equals v1e1 plus v2e2. In contrast, however, these v1 and v2 represent the measured values of the two contravariant components in this frame of reference. Now, even though we may sometimes draw these measured components in diagrams like this, it's not strictly an accurate way to illustrate this situation. You should realize that depending on the values of the basis vectors e1 and e2, these measured values of v1 and v2 could be bigger or smaller than shown here, and so this way of drawing the diagram is somewhat flawed. That said, we will probably use this kind of diagram sometimes for convenience, to save putting in the component vectors and having to relate them to the component measures. Anyway, having discussed the idea of the covariant derivative as it applied to one dimension, we want now to think about the covariant derivative of each of these two contravariant components of the vector v. If you like, we want to know the actual derivatives of the two contravariant components, v1 and v2, and because we have two independent directions to think about, that means we have four things to calculate, four covariant derivatives to work out, and that's for the contravariant components. dv1 by dx1, dv1 by dx2, dv2 by dx1, and dv2 by dx2. In other words, how v1 actually changes with respect to x1, how v1 actually changes with respect to x2, how v2 actually changes with x1, and how v2 changes with x2. It turns out that each of these four things involve both of the dimensions, x1 and x2. For example, the first one here, dv1 by dx1, is calculated to be this. Here is the actual value of dv1 by dx1. Here is the measured value of it. And all of this is what I'm calling the correction factor for the effect of this two-dimensional metric tensor, the wavy lines. You'll notice that even though this equation is calculating dv1 by dx1, the correction term contains v2, and also the derivatives of the metric with respect to x2. And also, of course, this metric tensor isn't simply the g11 that we had for one dimension. This has four components, each of which is probably changing with x1 and x2 at the point under consideration. On top of that, in this two-dimensional space, as x1 changes, even by a small amount dx1, and we move a slight distance away from the point, the x1 curvilinear coordinates may well be on a curve, and so the rate of change of g values in the x2 direction will also affect things. The whole equation here looks quite daunting, but I hope you can see that it has a vaguely similar form to the one we had for our one-dimensional case, which was this. The correction term has a half in there somewhere, and it has the inverse of the metric tensor, as well as its differential, in a much more complicated form, of course. Now, when we created that equation for one dimension, we went on to suggest the use of a shorthand for this correction part of it, namely gamma 1, 1, 1, the Christoffel symbol. By this way of thinking, if we were to work through all the mathematics for the two-dimensional situation, we could take the first covariant derivative, dv1 by dx1, and identify these two parts of it as two rather complicated Christoffel symbols. The first called gamma 1, 1, 1, and the second gamma 1, 1, 2. This equation for the covariant derivative dv1 by dx1 would then become this. Just as complicated, but perhaps looking a little more simple. The complexity has been hidden in the shorthand of the Christoffel symbols. Now there's no proof being offered here for this, and we won't try to justify the 1, 1, 1 here, which represents the 1s in this bracket, or the 1, 1, 2 here representing the 1s and 2s in this bracket. But I hope you can accept this shorthand is useful. However, that's just one of the possible derivatives for this vector v, the derivative of the v1 component with respect to the x1 direction. Here are all four of the covariant derivatives for the two contravariant components of this vector v in two-dimensional space. There's dv1 by dx1, dv2 by dx1, dv1 by dx2, and dv2 by dx2. And they're shown here with their Christoffel symbols identified. Or if we wish to hide the Christoffel symbols instead, get rid of all the details, things look more deceptively simple, the covariant derivatives being these. It should be obvious that the indices of all these Christoffel terms are different from each other, and they signify that the terms themselves stand for different numbers. Along with being multiplied by the measurements of v1 or v2, pairs of them in this two-dimensional situation add different positive or negative correction terms to the measured derivative in the equation and give, on the left-hand side, the actual derivative of the component vector. We will go through but not prove what these terms look like in a minute, but before we do, you should realize that these four equations for the covariant derivative of the contravariant components of the vector can be further simplified using the Einstein Summation convention. Working backwards to that convention means that we can write these four equations into one equation like this. Now, if you want to think through this in order to get practice at using the convention, you might start by saying that there is only one index here that is repeated, and it's on the right hand side. It's r. This means that the only summation within this is over r, and that's how we get two Christoffel symbol terms each time for these two dimensions. All the other indices here, m and n, are not summed but simply worked through, so that, for example, this is the equation for m equals 1, n equals 1, this the equation for m equals 2, n equals 1, this the equation for m equals 1, n equals 2, and this for m equals 2 and n equals 2. But as I say, each equation has the sum over r, which means that they each have two Christoffel terms, at least in two dimensions. So that's the four equations that you get for two dimensions for the covariant derivative of the contravariant components of the vector v. However, you may have realized that we could have done all this not by starting with the contravariant components of the vector, but by starting with its covariant components, the ones with lower indices, which are found by dropping perpendiculars. If you do work through all that mathematics, you get a very similar looking equation. This time we're dealing with the lower index components, the covariant components of the vector, and the sign of these Christoffel terms is now negative. I say these terms plural because once again we have a sum over r, which in two dimensions will produce two terms from this in each of the four equations that this all represents. Of course, even though the sign in front of the Christoffel term is negative, it may be a positive addition if the Christoffel term itself is negative. And you can perhaps see why it's important to try to get used to the Einstein Summation convention. We've ended up with what looks like two equations. the covariant derivative of the contravariant components of a vector, and the covariant derivative of its covariant components. They look deceptively simple, but in 2 dimensions, each one of these equations makes up 4 equations, giving 8 altogether. On top of that, the Christoffel symbols themselves within these equations are a bit of a mess. If we write down the expression for the Christoffel symbols in the Einstein Summation convention, it would be this. So that, for example, in 2 dimensions, just one of those Christoffel symbols, gamma 111, would be this. Clearly, this not only depends on the value of the metric tensor itself, seen here in the contravariant or upper index form, but it also depends on the ways in which the various components of the metric tensor change with position, the various derivatives of it with respect to x1 and x2. And this all means that if we wanted to calculate the covariant derivatives in this 2-dimensional situation, we would first choose whether we wanted the derivative of a contravariant or covariant component. This would then give us one of the formulae, let's say the one for the contravariant components. Then, if we wanted to carry on with this calculation, we would expand it out to the 4 possibilities, giving these 4 equations again. Then we would need to expand these 4 equations by putting in the various Christoffel symbols, and that would give us these 4 equations. And then, of course, we'd have to evaluate all the various parts of these equations, including working out all of these differentials, which come from the way the 4 components of the metric tensor change with x1 and x2 at the point. And all of that is just for 2-dimensional space. Wait till we get to 4-dimensional space-time. Now, don't be too put off by all of this. Try to see the overall sense of what each of these equations is saying. For example, the first one of the 4 says that in 2 dimensions, the actual rate of change of v1, the contravariant component of the vector, at some place, with respect to x1, the x1 direction, is equal to the measured value of that rate of change found by using the given frame of reference plus 2 terms. One term is the measured value of the covariant component v1 of the vector multiplied by various things related to how the metric is changing at that place. And the other term is the measured value of the covariant component v2 multiplied by some other things related to the metric tensor and how it's changing. In a way, these are the correction factors which make the incorrect measurement of the derivative become correct, and they depend on the metric itself, how it changes, and also on the measured value of the components of the vector v1 and v2 at the point under consideration. It turns out that very often these complicated equations will actually simplify. I mean, you only have to look at the Christoffel brackets to see that some things may well add up to 0, but it is still a mess. And if we had 3 or more dimensions, it would mean more equations, more Christoffel symbols in each, and more things within each Christoffel symbol to be calculated. And suddenly, I suppose the Einstein Summation convention looks rather nice. Here, once again, are all the equations for the covariant derivatives of the various components of vectors in as many dimensions as you like. And here's the expression for the Christoffel symbols in that convention. By now I hope you are beginning to get a bit of a handle on what all this means. And to sum up, firstly, the covariant derivative of a vector component is what we might call the actual way it changes with position, regardless of the frame of reference used. This is how the component of the vector really changes. Secondly, the measured derivative of that component, on the other hand, depends on the frame of reference being used to get the measurement. Thirdly, the Christoffel symbols, along with the measured values of the components themselves, help to provide the connection from the measured derivative to the actual derivative. Also, because the formula for the covariant derivative contains a pair of contracted variables which must be summed, or in this case, there will be 2 of these connection terms in 2 dimensions, 3 in 3 dimensions, and so on. And fourthly, on top of all that, Within each Christoffel symbol term, because of this sum over S, there will be 2 of these in 2 dimensions, 3 in 3 dimensions, and so on. Now in the next video, number 8, we will illustrate the importance of the covariant derivative, and we won't need much of this detail. What we will need is the basic idea of what it all means, and that is encapsulated in these few sentences. We're going to be thinking about how objects travel through space, and in particular, we want to find the minimum path length between 2 points, known as the geodetic. In order to find that minimum path length, we will use the standard calculus trick of differentiation to find the turning point, and then equating that result to 0. However, if curvilinear coordinates are being used, it means that straightforward differentiation, what we've always used from high school onwards, will not be good enough. We will need to use the covariant derivative, which will compensate for the stretches and contractions of the basis vectors. We will start that discussion by first thinking about geodesics in general, and then we will be able to go on to think about how distances from one place to another can be optimized using this special form of differentiation, the covariant derivative. This video number 7 centered around the covariant derivative and the associated Christoffel symbols. In the next video number 8, we will have an introduction to geodesics in spherical space and the tangent vector, and that will lead to the equation of the geodesic.